In this video, we'll talk about derivatives of exponential and log functions. Let's start with e to the x. It's probably the easiest function to take a derivative of because it's simply itself. And no matter how many times you take the derivative, you get e to the x back. Now, the powerful implication of this is that not only e to the x is growing exponentially or relatively fast, but also its rate of change is exponential as well. Now, unfortunately, other exponential functions are not as easy or straightforward, but they're relatively similar. If you take a derivative of a to the power of x, any other base than e, then it becomes itself, to start with, a to the x, but we multiply it by ln of the base. We actually do not need it with e to the x because ln of e is 1. They cancel each other. They're inverse functions of each other. But with other bases, we do need them. So let's do some quick examples. Let's say if y equals to 3 to the x, then what's the derivative? It's 3 to the x times ln of the base, which is 3. And typically we'll leave it like that. There's not a whole lot of we can simplify with exponential functions. Same thing with y equals 5 to the x power. The derivative is 5 to the x power times ln of 5. And again, it's okay to leave it like that. Chain rule, in a lot of situations, particularly in applications that we're going to discuss in this section, we have not just e to the x or a to the x, but we have e to the function and so on. So how we would use chain rule in this case, if we think about f of x as the inside function, so as we literally think of it as inside of the exponential. And the exponential would be the outside function. So again, let me write this as outside. So we apply chain rule is exactly the same way as before. It's the derivative of outside, which is e to f of x again, the same exact thing we started with, times the derivative of the inside function, which would be f prime of x in our case. So let's take a look at how do we apply it. Here is a quick example. If we have e to the power 4x, how do we take the derivative? Again, if we follow the structure above, which is the chain rule, it would be itself e to the power 4x times the derivative of 4x, which is 4. A lot of times what we can do is we can put that constant or the derivative on the front just to clean it up a little bit. So that the derivative becomes 4 e to the 4x. Now let's take a look at a few other examples. If a function is e to the x squared, what's the derivative? Well, again, it's itself e to the x squared times the derivative of x squared, which is 2x. And once again, we put the 2x on the front, and we get 2x e to the x squared. What about e to the x plus 3? Well, again, it's itself e to the x plus 3. And then what's the derivative of x plus 3? Derivative of x is 1, and 3 is a constant, so it's gone. So here we just get 1, so we get the function itself, e to the x plus 3. What about the next example, e to the 1 minus x? Pause the video if you haven't already, and try to figure this out before looking on. And let's discuss this. It's e to the 1 minus x times the derivative of 1 minus x, which is negative 1. So we can put the negative on the front of the function. Now, chain rule for exponential functions of other bases works very similar. Again, let's focus on the derivative of the outside, which is, let me write it, it's this piece right here. It's basically exponential, again, is the outside, so it would be itself times the ln of the base, if you remember with simple functions, then times the derivative of the exponent, which is f prime of x. Now let's keep going. So let's try it with 7 to the 3x plus 1 power. Again, we get it itself, 7 to the 3x plus 1 times the ln of the base, ln of 7, times the derivative of 3x plus 1, which is 3. And again, we can simply rearrange some things. Let's be careful not to multiply them because ln of the 7 is inside of the ln, which is a function, so we cannot actually multiply it by 3, and so on. So 3 is a constant on the front, ln of 7 stays, it's another constant, we're not going to simplify it, and 7 to the 3x plus 1 also stays. Same thing with 4 to the negative 5x plus 2 power. Again, how we take the derivative. Again, if we focus on the outside first, typically I copy itself, the function, times the ln of the base, which is 4, times, think about it, what's the derivative of the exponent? It's negative 5, and again, we rearrange it a little bit and put the constant and the ln of the base on the front. Okay, same thing with 2 to the x squared minus 1 power. We get 2 to the x squared minus 1 times the ln of 2 times 2x. Again, do not be tempted to multiply it out. If you put ln of 2 in your calculator, you get a decimal. So that's how you could do it if you wanted to. But again, we can put 2x in the front times the ln of the base times 2 to the power of x squared minus 1. And again, you can pause the video and see how it would work with 3 to the x squared minus x. And it works very similarly. If you notice, it's itself times the ln of the 3 times 2x minus 1. And this time the 2x minus 1 is in parentheses because we're multiplying and it's more than one term. And again, we can put it in the front, rearrange it a little bit. Next, I'd like to discuss in this video is how to take derivatives of log functions. They're similar to exponentials, except I usually remember it has to do with fractions. Again, the ln of x, which is actually log base e of x, if you think about it, so base e, again, makes it a little bit easier. Here we just get 1 over x. We're not going to discuss why that is, but we're going to take it for granted for now. 1 over x. So, derivative of log base a of x, again, is very similar, but it's 1 over x like ln, except it has ln of the base attached to it, which is similar as with exponentials with other bases, except in denominator. That's how I remember. Again, there's a few simple ones. Let's go over some quick examples. The first few are ln of x, where we do not need chain rule yet because it's just ln of x, but we do need several rules. Like, for example, 3 ln of x. If you notice 3 is a constant in front of it, we can use constant multiple rule as opposed to constant itself, which would have been 0. But we can do constant multiple, which we can take the 3 down and keep it. Derivative of ln of x is 1 over x. So it should be 3 times 1 over x, which is 3 over x. Okay? What about x times ln of x? Again, if you pause it, but if you think about it, it's a little bit different than the example above because x is a function and ln of x is a function. And if you think about it, it's actually a product of the two functions. And we can use product rule. So if you recall product rule, let's take a look. We take the derivative of one of them at a time. Let's take the derivative of x first, which is 1, times, keep the second one as original, ln of x, plus, now we keep the x, and the derivative of ln of x is 1 over x. And what can we do? We can cancel the x's here. 1 times ln of x is just ln of x, and that would be plus 1 that's left over. So sometimes we can use product or quotient rule just the same way. What about if it was a log of base 2 of x, for example? We'll apply the rule for other bases, which is 1 over x times ln of the base. The base in this case is a subscript that you'll see, and that should be ln of 2. A lot of times on all the logarithms, they have a base. If you ever see log base x in some textbooks, they do not put the base. It means log base 10 of x. So we may see that sometimes. So what about chain rule? Again, if ln is the outside function of f of x, we can take derivative of ln portion first, which is 1 over f of x, times the derivative of what's inside of the ln, which is f of x, that would be f prime of x. Here, occasionally, we can cancel something. But if we cannot, then we can put the derivative over the original. You can also put the derivative over original and then cancel, so you can do it in different order. Same thing with other bases. The derivative of log base a first, which is 1 over the function, times the ln of the base, times, now it's the derivative of the function itself. And again, you can put it on the top and cancel if you need to. So let's take a look at ln of x plus 3, for example. So we get 1 over x plus 3 times the derivative of x plus 3, which is 1. So we simply get 1 over x plus 3 here. Nothing to cancel. What about log base 3 of x squared plus x? Again, we take the derivative of the log portion first, which is 1 over. Now we put x squared plus x in parentheses because we're multiplying. And times a ln of the base, which is a ln of 3. Times the derivative of x squared plus x, which is 2x plus 1. And again, nothing to cancel here unless you could factor something out and divide by it and cancel the top and the bottom. Typically, we cannot cancel. But occasionally you can if you're multiplying. If you get something like 6 over 6x, for example, you can simplify it, the 6's, so you'll get 1 over x. Again, that's just an aside, but in this case we couldn't cancel anything. Now, occasionally we'll see a ln or other logs of absolute value of x, which would show up. So at first, I would like to show you guys why we get 1 over x as if there was no absolute value. We can use chain rule here. So if you recall with chain rule, it would be 1 over the function, which is 1 over absolute value of x, times what's the derivative of absolute value of x? As you can see here, it's absolute value of x over x. That's something we discussed in 4.1. So notice how you can cancel absolute values, so you'll get 1 over x. Again, for domain purposes, sometimes we include absolute value, and in the examples you'll see that, because with absolute value, you do not have to worry about negative numbers, either for the derivative or the original function. So basically, we treat it the same way. And let's say a ln of absolute value of 2x minus 5. We treat it as if it was just a regular 2x minus 5. As you notice, absolute value cancel. So it would be 1 over the function, which is 2x minus 5, no absolute value, times the derivative of 2x minus 5, which is 2. And so we'll get 2 over 2x minus 5. Again, do not be tempted to cancel the 2's, because we cannot factor it in the bottom. And that's it. And now pause the video, see if you can do a ln of x squared plus 4 with an absolute value. Now if you've come back, you'll see it's 1 over x squared plus 4 times 2x, and again it's 2x over x squared plus 4. Similarly with a ln of absolute value of 5 minus 9x, and we'll get negative 9 over 5 minus 9x. Now let's take a look at a couple of applications. In fact, there are 3 on your homework, one with a ln that we discussed in class, but in these notes there are a couple of exponential ones as well. Like for example, the average price of a 2-bedroom apartment in uptown New York City during the real estate boom from 1994 to 2004 can be approximated by, and we have a price function, which is already average price, equals to 0.14 e to the 0.10 t million dollars. And again, the years are from 1994 to 2004. So t is time in years, so you'll see that t equals 0 represents 1994. What was the average price of a 2-bedroom apartment in uptown New York in 2002, and how fast was it increasing? So if you notice, it's actually a 2-part question. We're asked about what was the actual price and how fast was it increasing. So to find the actual price, we can figure out we need to plug in t equals 8, because 8 years passed since 1994. We can plug it in the original function. On your calculator, you'll probably see second ln that you can press to find e to the power of x. So press second and then ln. Okay? And when you input this, you can do it all at the same time. Now, the way I would put it in is probably 0.14 and then e. Depending on the version you have, you may have the exponent as an exponent, in which case I would just put in 0.10 times 8. Or you may have the older version, which looks something like this, in which case I would put it in parentheses, 0.10 times 8, then close parentheses. Either way should give you the same answer. And in the homework, it's asking you to do it to 2 significant digits, which means non-zero digits after the decimal, which in this case is $0.31 million. For the exam, you can actually multiply by $1 million and get it a little bit more exact. Okay. Now, to find out how fast it's increasing, we need to first find the derivative using what we've learned. So if you notice, 0.14 is a constant on the front. It's a constant multiple, which we keep. Then we take derivative of the exponential, which is itself, if you remember, times the derivative of the exponent, which is 0.10. Now we have two constants here, 0.14 and 0.10, which we can multiply, and we'll get 0.014 e to the 0.10t. Again, we can plug in 8, and this time the two significant digits, now notice there's two non-zero numbers, but there's actually three decimal places here because of the zero. So this would be considered two significant digits. And again, it's $1 million per year, actually, because it's a rate. So it ends per year, and that's how fast it's increasing. Now, here's a little bit more involved, but this is the last application we'll talk about. What if there is an epidemic in 2003, and the number of cases is increasing by about 4% each day? And on April 1, 2003, there were 1804 cases. Find the exponential model that predicts A of t, people, amount of people infected t days after April 1, 2003, and use it to estimate how fast the epidemic was spreading on April 30th, 2003. And round your answer to the nearest whole number of cases. Now you do have a choice how you set up the exponential. You could have used A of t with the e equals to a0 e to the kt, but in that case usually you have to solve for k. Sometimes it's close to the percentage, sometimes it's not. Or we can come up with a different base, just as practice. So notice it's the same initial amount, A0, which is 1804. That's how many we started with. Why is the base 1.04? Well, at t equals 0, we'll get 1804 because anything to the 0th power is 1. But at t equals 1, there is 4% increase. How do we typically find 4%? We multiply 0.04 by 1804. And then we would add it to 1804. So I'm going to put 1804 on the front plus 0.04. So if you notice, it's actually, if you factor it out, 1.04 times 1804. That's how you can find out percent increase because you add it on top of the original. So you'll get 1.04%. You can actually check it, how many would be in one day. So you can add any percent increase on top of the 1 to get that the base that you need. So how fast was it spreading? We would need to take the derivative, which is again a constant, 1804. We keep it the same. Then remember, exponential, 1.04 to the power of t, it stays, times, if you recall, we need times ln of the base, which is ln of 1.04, times, if you were using chain rule, derivative of t, which is 1, but we don't need chain rule here. And that's it, really. I mean, I guess you can multiply through, but that's really the function. And why do we plug in t equals 29? Well, if you think about it, if April 1st is t equals 0, then April 2nd is t equals 1 day since April 1st. So April 30th is 29 days since April 1st. And we can plug in 29, and we get approximately 221 new cases per day, and that's rounded to the whole number. And that's it for this section.